Before we start the content of this video, let's review where we're at. This will probably be the final part of a 4-part series. In part 1, we discussed the board itself, the Maduino Zero board. And we discussed how the Maduino Zero board has the SIM7600 module, which allows the GPS data collection and also the 4G LTE connection. The next thing we did is we talked about AT commands, and we discussed how that was the mechanism to get the SIM7600 module to perform certain actions. Then we discussed what commands to send to collect the GPS data, and then we also discussed what commands to use for us to send the data that we collected to the HTTP endpoint. Also in part 1, we discussed the importance of object-oriented programming and how we were going to encapsulate all these features into their own classes. And then in part 2, we did a deep dive into various sleep modes, and I collected a lot of data showing which sleep modes were better under certain circumstances. And in part 3 of the video, we introduced battery monitoring. We then used that battery monitoring feature to enable low power modes when that battery got below a certain percent. In addition, we added a feature to send SMS text messages. So, for example, if the battery got below, say, 10%, text my phone where you're currently located at so I can change your battery. In this video, we're going to introduce a few new features and wrap up a few loose ends. First of all, we're going to introduce parsing the GPS data on the board. So far, the data that we've collected, we just left it in string format. In this video, we're going to parse that string and get lat long and altitude. In addition, we're going to use that data to calculate distance and velocity. And finally, we're going to use our newfound data to introduce the concept of a dynamic GPS sampling. So instead of using a periodic sampling rate, say every 15 seconds, we're going to use our velocity calculation to sample at a rate where we get a point, say, every 50 yards or 150 feet. The ability to leverage this dynamic sampling rate can extend our battery life because, if we're just kind of sitting stationary, we don't have to sample, even at 10 seconds, 15 seconds, 60 seconds. The board knows it's not moving, so it can set the sampling rate to 2 minutes or 3 minutes. And then once the velocity starts to move again, then we can increase the sampling rate down to kind of the resolution that we want. All right, before we dive into the code, I just wanted to remind everybody that this code is uploaded to GitHub. So if I cover something too fast and you didn't quite see it on the screen, you can always go here and grab the versions. I did enter different tags for the different versions that we've been doing so far. I haven't entered the tag for this current version, and I will do that after this is completed. So let's look at some of the new code. I introduced a config class. One of the criteria I use to determine if I'm going to put stuff in a class is if I were to put it in a class, would it make the code cleaner? And in this case, I believe it does, and also it allows me to do future things if I wanted to. So I pulled all the configuration data, all the values that we can use to change how the board behaves into one class. This is the definition of that class, and you can see the points. I'm not going to spend too much time here because really the implementation is pretty much the same thing. It's just kind of setting all of these variables. The top 3 are for the battery monitor that we introduced in a previous video. The next 3 are for the API. So it has like the endpoint, the URL, how many points we want in every single, every payload that's sent to the endpoint, and then the max number of points. So we kind of put some cap on how many points that you can send. And then the last variables all control the GPS. These top 2 are going to be used when we compute a recommended GPS interval based upon the velocity. We introduced the low power battery mode a while back. This is the low power battery mode sampling rate. So when we enter low power mode, which we set up here at 5%. So if we get down to 5%, we enter low power mode, and then we switch to only sampling the GPS at this rate. The next one is a new variable, and this is the ideal spacing that we want. And this is going to help us when we compute the recommended sampling rate. What we're trying to get is an ideal sampling distance of about 150 feet. And so every 150 feet, ideally, we're getting a GPS point, and we're doing this based upon the velocity computation. These next two, they work in combination with each other. This is the threshold distance in feet that you have to move for the new point to count. So if I'm sitting stationary and I haven't moved more than 10 feet in this case, then the new point won't be cached and it won't be added to our data. However, if I'm stationary for more than 120 seconds, then I will count another point. So there is a threshold in when the last point was collected. So we're going to see how these are used later on when we're collecting the actual data. There's also a new math file. So it made sense to put this kind of stuff in a place where you can reuse it. Think larger than the project that you're currently on. You could inline these into various things. But if I'm really building this, it could be that I'm building other boards and this is my math library. And so in the future, if I have a board that I want to convert degrees to radians or meters to miles, I already have that code written. I can pull this class into that project and have these reusable objects. So that's what this class is. I'm just putting some math into one place so that I could reuse it into other projects if I wanted to. So it defines a couple of things. First of all, there's a constant, the Earth radius in miles. We'll see how that's used later on when we compute the distance between two GPS points. And then there's a couple of helper methods. For small functions like this, I tend to just inline these. So you can see there's three functions. One converts degrees to radians, another converts meters to miles, another miles to feet. In this class, I'm also using the YAGNI principle. YAGNI is an acronym for you ain't gonna need it. And you can see I have a convert degrees to radians feature, but I don't have this function convert radians to degrees. I didn't spend the time writing that because I don't need it at this point. At some point when I do need it, it's easy enough to add, but I'm not wasting my time on this project, building stuff that I just don't need. So the implementation of the math is pretty simple, and it only involves me setting this one variable. And so I set the Earth radius in miles. So the next class we're going to cover is this date time class. This is just a simple wrapper. I know that in the GPS string there's a timestamp in there. And so this class, the intent of this class is it's a very simple wrapper, not a lot of features, just to hold that data. So when I parse that string, you're going to see there's a year, month, day, hour, minute, second in there. This is the class that's providing me structure and places where I can store that. There are a couple of helper methods down here, and we'll talk about these when we look at the code itself. So let's look at the implementation. The implementation has a couple of constructors. There's a default constructor that just sets everything to 0. Then there is a more detailed constructor where you could actually pass all the values in: year, month, day, hour, minute, second. Sometimes I don't know what they are yet, but I need a value, and then we'll see that in a little bit. So I just initialize everything to 0 here. And if you already have an instance of this class, this is just a quick setter method where you can pass in year, month, day, and you can change the values that you currently have. So the next function that you see here is a 2 seconds helper. And for this class, I did import another library. I imported this library kind of late in the game. I probably could just use this library itself to hold my date time data, but I'm just using this library to compute the number of seconds. That computation is kind of complex if you start to look at leap years and, what's the reference, how many seconds since a certain time period. So I'm just using this library to compute it in a standard way. The next method is a little helper method. So given the date time that I currently have, if I fed another reference in, then I can subtract the number of seconds from each of them to get the difference. So this is just a differencing method. So the next methods in this class are a couple of string helpers. In fact, there's 4 of them. So there's just a number of different formats that I was using for outputs. And so these are just little helper classes to convert this date time structure to a string in different formats. And then there's a helper method here that converts the month number, 1 for January, to the actual month name, which is the string January. Then there's a private helper that validates the data that's in the structure to make sure everything makes sense. So I don't have a month value that's, say, 13 or 0 or something like that. And I can use this to determine if I have a valid date. This is a public member. So we go back to the declaration. There's a public member where I can get access to this, and you'll see that being used later on. So that's it for the date time, really just encapsulating some year, month, day, hour, minute, second data that we're going to collect from the GPS string itself. So the next class we're going to review is the GPS point itself. And just like we talked about previously with the date time, this is really just encapsulating lat, long, and altitude. And here you can see that we have an instance of the date time class also. A couple of static methods here at the top help us convert the NMEA formatted string into the actual lat, long, and altitude. We'll see the details of that implementation when we look at that later on. 3 different constructors, again, depending on the data that we have. If we don't have any data at all, we'll initialize things to zeros. If we have just lat longs, we can initialize it, but if we have all the data, we can create an instance of this thing. And here we see another instance of a string helper, right? So I want to take the data that's in this object and I want to print this out so I can see what it looks like. Here's an implementation to compute the distance from our current lat long to a previous point. And we also see that we have a helper method to copy one point to copy the data from one point to this data. And then finally, there's a validate method. So if we look at the implementation is pretty simple. So we'll cover the first 2 and we'll go top down. But first, let's look at this. This is the format of the string that we're actually getting. And you can see, here at the very front of this, there starts to be some comma separated data. And you can see all the different parts. So this part here, this is the latitude, and then it's either north or south. And then the next part is the longitude, and you can see, you'll see either east or west here. So this next bit is the part of the timestamp. It's date, month, year, followed up by the actual hour, minutes, and seconds. And then there's a parameter here for altitude. So that's really what we're parsing in here. And so this first function is helping us just to convert this NMEA format for lat and long, and we're going to convert that into a number of degrees. And so that's what we're doing up here. We're taking this number, which is in this format, and we're converting it to the number of degrees. This is the main function where we're actually converting the string that we're getting out of the SIM7600 module. And again, that string looks like this, and we're parsing that out. And so I'm not going to go into all the details. There's a lot of little nuances here where I'm looking for different tokens, and then I'm grabbing where that token is, and then I'm taking a lot of substrings. Here you can see me calling this helper method at the very top here to convert that substring that I got for the lat string, which is right here. I'm putting that into our helper method and getting actually the latitude out in degrees. And then the next little bit is I'm starting to look at is this thing, if this is north or south. If it's south, it's negative. I turn it to negative. And I do the same thing for the longitude. So I grab this next substring, I send it to our converter method, and I get the actual degrees out. And I'm looking for the east or west token. And if it's west, I set it to negative. And I do the same thing for parsing out the day, month, year, and the time value, which is hour, minutes, seconds. And then finally, I parse out the altitude. So if I have a GPS sentence that has the starting token that I'm looking for, then I parse out the values, and I replace these default values with the values that I found in this sentence. And then down at the bottom, I create a date time structure from the data that I just computed. And then I create a GPS point from the data that I just parsed out. And I return that point. So that's what this helper method does, is it parses this GPS string, this sentence, and I convert it to one of our GPS points. So we just covered those 2 static methods, which kind of do the brunt of the conversion of the string. So let's look at the constructors. So there's 3 constructors. They're pretty simple, just varying amounts of information that I know. So if I don't know anything, I set everything to the default values. And here you can see I'm using the default constructor for the date time option also. Here is the copy method. So if I want to copy one point to another point, then I can call this method, and you can see I'm defaulting to, I have a date time, so I'm setting the values to whatever the other point is, and I'm setting the lat long and altitude to whatever the point values are. And it's important that I validate. So again, we'll cover the validation, but it's the same thing as we saw in the date time. I'm just making sure that the numbers that I have are in the range that I expect. And then there's a public variable. You will see that it's public here, that it's accessible outside of the class. And so you can determine if the current point that you have is valid. And that's important. We'll use that later on. And then there's two helpers. Here's a string helper. So if I ever want to kind of visualize this or serialize, print this to the USB or the console out, then I just call this method and I can get a nice string of what this data looks like. And here's a helper, and we'll cover this class in a second, but this is a helper for, given the current point, what's the distance from this point to another point. And so I'm just deferring this to another helper class, which we're going to cover in detail next. All right, next let's look at that GPS calculator class that we saw previously. The intent of this class is to encapsulate the calculations that you can do between 2 points. And so here's some of the data that we can start to see. First of all, there's a public is valid Boolean. So there's a flag that tells me, is my computation valid or not? Here's the distance in 2 different measures, so in miles and in feet. Here's the time difference, but in 2 different measures, in seconds and in hours. And then here's the velocity in 2 different measures, in miles per hour and feet per second. And then finally, we'll talk about this. This is the recommended GPS refresh period in milliseconds based upon our configuration data that we set earlier. And let's look at how that's computed in a second. There's a constructor and a toString helper, and here's where the distance calculation is really done. We're using the haversine calculation. It's fairly accurate for the model that we're dealing with, and so this is a simple calculation that's easy to implement. So now let's look at the implementation of this GPS calculator class. Most of the work is done in the constructor here, and so the constructor takes 2 GPS points, and it's going to compute all of the variables, which I initialize here to either 0 or false for the isValid flag. But given these 2 points, we're going to compute this distance. And so the first thing I do is I inspect those 2 points and make sure that they're valid. So if both of them are valid, then I can feed the point data into the haversine calculation, and we'll look at the details and how that's implemented a little bit below. But essentially, it's taking the lat longs from both points, and it takes the Earth radius in miles. The output of that calculation is going to give me the distance in miles, which I can use my math library here to convert to feet. So as part of the GPS sentence that we get, we actually have the timestamp in there. So we're going to compute the difference in seconds, and here I'm just using the difference helper that's part of point 1. I'm feeding in point 2, and I get the difference in seconds. And then I convert that difference in seconds to the difference in hours. And finally, I'm going to use this data to compute the velocity in feet and the velocity in miles per hour. So if the time difference is equal to 0, I'm just setting the velocity to 0. Otherwise, I'm going to use the distance in feet that I computed and divide it by the distance in seconds, and I'm going to get the velocity in feet per second. And similar thing here for the miles per hour computation. If I am in here, I have 2 valid points, then this computation is going to be valid, and I'm going to set it equal to true. And then down here, I'm actually computing a dynamic GPS refresh period based upon these 2 points. So given the velocity in feet per second that we just computed, if it's 0, I just set this recommended GPS refresh period to the default value, which is in my config file. Otherwise, I'm going to use, so the ideal distance between points and the velocity that I just computed to compute a desired or recommended refresh period. And then lines 35 through 42, I'm just clamping those to our smallest GPS period or the default. So nothing, it can't go any faster than the smallest GPS, and it can't be any larger than the default period. And again, these are in my config file, and so you can set those in one spot. And there's not much remaining in this class. There's a string helper. And again, these are nice to have if I ever want to print out, what my last calculations were. And here's the haversine calculation. I'm not going to go over the details of this. You can look this up online and find many references for the formula for this. But essentially, you're taking an ellipsoid and given a lat long and an ellipsoid, you're doing some math to figure out the distance between those 2 points. So the Earth isn't truly an ellipsoid. So there is some slight error, but the error is pretty minimal. And so this is a fairly accurate calculation for that distance based upon the Earth radius. And the last thing we're going to do is we're going to look at how that changes our main CPP file. And so at the very top, you can see that I'm importing all these new classes, the date time helper, I'm importing the math helper, the GPS point, and the GPS calculator. And then as you scroll down, the next changes that we'll see are these 2 new points here. I'm storing whatever the new point is, and I'm also storing the very last point that got cached. And so in the main CPP file, I know what the new point is. I just got it from the GPS. And then I also will know what the last point cache was. We'll see how we use those in a little bit here. But there are 2 new variables that I'm introduced here that are used to track those 2 points. There's also 2 new floats here that we're using to cache distance. The first one holds the total distance traveled in feet since the board got started. And this last one is the total distance traveled for all the points that are in the last post. So, if you get a post that has 30 points in it, then this is the number that is the total distance traveled for those 30 points. So if we keep scrolling down, line 77, there is a small change here. I added a new helper method on this file helper, which is the line counter. So when this thing starts up, if there was 30 points already in the file, now I know that there was 30 in there. Originally I had this just starting at 0, but it's not really true, in situations where, the board got shut down before it got a chance to post data. And so there might be some data in the GPS file and that little local cache. And so this is the number of points in the local cache when we're starting the board up. So let's take a look at our loop here. And I'll highlight the changes, but also let's just kind of point out where we're at. At the top of every loop, I refresh the battery monitor data so I know what percentage we're at or if we're at low mode. Then I can do some low mode options here. So if the battery is in low mode, I can use the low mode battery sample rate, or I can sample a little faster if I'm not in low battery mode. And again, here was the low battery mode option where, if we haven't entered low battery mode the very first time we do it, I send an SMS, and it can be to an endpoint where you can say, hey, come find me and change my batteries. So our next area where we've changed slightly is on line 119. And let's go ahead and look at the implementation of our GPS class here. Slight change in here. Previously, when we collect the GPS point, we send the AT commands. So I end up here with this location data. And again, this was the GPS sentence that we had before. But now we have this ability to parse that sentence. Within this class, we're actually using that parser from the NMEA string. So I'm sending that string in and I'm getting an actual point back. And I'm caching that point into our local cache. So a new member on this is I'm not only storing the GPS sentence, which is what I stored before, but now I'm storing what that point, the last point was. And so this is the point, the parsing of that GPS sentence. And you can see that parsing happening right here on line 53. I'm parsing that structure into the point and I'm copying it into our local point there. So after I collect the point, I am using that last point. And again, I'm using another copy. I'm pushing this data around into the different structures that we have. This is the copy that I have at the very top that I'm trying to hold on to, whatever that new point was. I may not need this variable, but it just makes more sense to me to have that around. I'm using one of my string helpers to print that new GPS point out. Here's I'm using the validation. So if I have a valid new point, I come in here and I use my calculator to calculate everything it does. So I send the new point, I also send the last point, and I get a calculation. Remember, this calculator takes the 2 points. If one of them isn't valid, the calculations will all be zeros. But if I got a new valid point and I got a valid last point cached, then I'll get the distance out. And so here you can see an if statement. I end up in this area, 3 possible conditions. Number 1 is I don't have a last point. So the very first time I start this board up, this is the condition that's going to be met. I don't have a last point, but I have a valid new point. And so I end up in the main part here. The second way to get into this, enter this if statement, is if my calculated distance is greater than the threshold that I set in my config file. And the third way is if my calculated time difference between my last point and my new point is greater than that threshold I set in my config file. So either if I've gone far enough or if I've been sitting stationary for long enough, I'm going to end up here, or if it's my new point. So once I'm in here, instead of caching to my SD card that GPS sentence, the NMEA format, what I'm doing now is I'm caching a format that I can control. So I'm using this string helper that's part of my new point, and I'm caching that to my SD card. If that succeeds, then I copy the last point. My new point is now my last point that I cached. And here's where I'm incrementing the distances, those 2 variables for the distances that I'm keeping track of. The total distance that's been traveled since the board got turned on. And this is the total distance traveled since the last time that we posted data to our endpoint. This is the same as before. I'm tracking the number of points in the cache, and I'm telling the board, hey, you've got a valid point this iteration. You can go to sleep if you need to. So if I fail to get into this if loop, I do just print out to the console. So if I'm watching this to debug it, that new point wasn't far enough away. So, and if I had a valid calculation, I'm doing 2 things. I'm console writing out the velocity and the distance that I traveled, and then I'm setting this GPS refresh period. And if you recall, we just did that a moment ago up here. This time on line 109, I set it, if I was in low battery mode, I either set it to the low battery mode value or the default value. If I end up with a valid calculation, so now you can see here on line 165, if I'm in low battery mode, I don't do anything different. I set it to the low battery mode refresh period. However, if I'm not in low battery mode and I have a valid calculation, this is where I'm using my recommended GPS refresh period. And that calculation, if you remember, that was based upon the velocity that we traveled and also the ideal distance that I want between my points, which is in my config file. And if you recall, that was set to 150 feet. So this allows us to dynamically set our GPS refresh period to, kind of conserve our battery, but also to get the most resolution that we want on the data trail that we're collecting. So just a quick review here. I don't think much has changed. This is where we're actually taking the data that we've collected and we've cached it on the SD card, and I'm going to pull the data off and send the data to the HTTP endpoint. So here's if my number of points cached is greater than whatever we configured. So you say 30. If I have 30 points in a cache, I'll enter this loop. If I have cellular connection, I'll get the lines off the cache that I want, so the 30 points. If I have lines that come in here, and this is where I post the data. And then the only thing that you will see that's new here is, after I post, I set my distance traveled since the last post to 0. And so that's where that gets reset. Everything else is the same all the way down through here. And these 2 lines are the same as before. And then we come down finally to our sleep mode, which is the same as before, except it's now using our dynamic GPS refresh period that we've computed. All right, let's plug this board in and we'll power it on. And then let's come up to our code. Let's compile and upload the code to the board. So it'll do a quick build, push it on over, and then let's start the the terminal so we can see the console out. And while that's doing its startup stuff, let's go ahead and just do a quick review while we got this in front of us. This is the Maduino board. It's got the SIM7600 module, which we talked to through a serial connection from the Maduino board to the SIM7600 module. And this is where we send those AT commands to. I'm programming this and powering it through this USB-C port. And then it also has a battery plug right here. So standard battery plug, you can see this battery, push it in the screen. This is the battery I've tested, and you can plug other batteries into this thing too. When the USB-C port is plugged in, it does charge this battery, and we'll see that in a little bit. Antenna-wise, this is the GPS antenna, and you can see the standard kind of square GPS antenna over here. And you can see the two LTE antennas here. So there's one as a primary, I forget which one's primary, which one's secondary, but the two antennas are there. So if we look at what's on the output, so once the board's restarted, we can start to see some of our output here. It didn't capture the right in the beginning because at the very top, sometimes the serial port isn't open for USB, and so you're writing to it and nothing's showing because it's not quite initialized yet. But you can kind of see the trailing edge here. The SD card's initialized, some 7600's initialized. You can see the hardware IDs. Here's where I print the battery data out if I was collecting it. I'm not currently in the mode where I'm collecting battery data. And then what we're going to start to see is we're going to start to see each one of these lines for every type. It's at the top of the loop. So after we start it up, you can see it hasn't found a point, hasn't got the GPS satellites, doesn't have enough GPS satellites yet to give us a point. Eventually it does get us a GPS point. This is not the NMEA sentence that comes out of the module. This is our formatted version of this. So we formatted this and we cached 1 point because we've configured up here that once we get 1 point in the cache, go ahead and send those points to the API. It does make an API call. And then it's allowed to go to sleep for the first time. And you can see here, because it only has 1 point, it's just using our default 5-second interval. The next time it wakes up, it does the battery again. It does find a new GPS point. The distance away is 1.74 feet, so it tells us this is not far enough away for it to count this point, so it does not cache it. So there's 0 points in the cache, and it goes back to sleep. The next point it captures, so you can see here it's only 2 feet away, and so it's still not far enough away for it to actually be cached, and so there's 0 in the cache, and it doesn't send anything in the API. The point after that is 3.3 feet away, not cached. It's the same thing again, it's not far enough away. The next point after that is 3.2 feet away, and again, it's not cached. At some point, we'll either hit the 122nd time period, and it'll cache a new point, or it will be far enough away. Here's one that's 9 feet away. Still didn't cache it. It didn't break the 10-foot mark. Here's one that's 11 feet away. So this one, you can see it did cache it, and it did send it up. Now it has 2 points based upon our velocity. We're not really moving, so it's going to go to the maximum that it can, which is the 5,000 or 5 seconds. This one's not far enough away. It didn't cache it. And so you can kind of see, just looking at it, the operation of what's happened. It's always caching or getting new points. It only captures or caches that point if it's far enough away, if it breaks the threshold, or if we broke our time period. And you can see how it's just operating here. All right, before we completely wind down this project, let's just kind of review maybe some possibilities for the future here. My intent is to move on to an ESP32 board that I have, but I wanted to leave you with maybe some ideas that you might want to follow up. So first of all, there's some enhancements to the board itself. I think that, possibly a shake awake feature might be useful. So, the board goes into almost a power off mode. So even the MCU itself is powered off, and you have some external circuitry where you kind of have a sensor accelerometer or something, and you shake awake, and then it turns the board on. And then once the board's on, then it stays awake for a certain threshold or a certain time period. Adding other sensors, I think, is also kind of interesting. As you collect data for the GPS, maybe you want to know something else about the environment, maybe humidity or temperature, or whatever else you can think of to add to this. I think that the low power option is still a little bit of a concern. So right now, the lowest power option that we have is when we turn the SIM7600 module off and we set the MCU into deep sleep mode. Even when we're in this mode, the board still draws around 10 milliamps, 10.7 milliamps, and at the 5.08 volts that we're getting from the USB-C port, that's still around 54 milliwatt hours of power that the board's consuming. And that's the best that this board can possibly do. Like we talked about earlier, maybe the shake awake feature, you can add some external circuitry, but you're starting to get some complexity there that maybe it's better just to switch to a different board. So that's kind of what I'm going to start to explore next, is I want to look at the ESP32 board. Nothing wrong with the Maduino board. I've loved the programming on it, but I'm just interested to see kind of what the ESP32 board can do also. And there's another half of the development still left to do, right? So we've been working on the board. It's been posting data up through HTTP to a website hook that we've just kind of been using. But the reality is if you were building this thing yourself, you would have to build that website. And I do a lot of website development as my full-time job. And one of the things that I'd be interested in is if people are interested in seeing, that other half being built. So if you are, let me know in the comments, and possibly can queue that up. But some of the features that website could have is obviously we'd replace the endpoint with our own, so it wouldn't post data to the website that we've been using. One thing the board should always do initially is kind of do some registration with our website. And so the board knows the IMEI number and the manufacturer and the model number, and that should be unique to every board. So with those 3 bits of information, when this board gets powered up, it should hit an endpoint that sees if the board's registered. If it's not registered, then there should be a registration process that happens where you end up setting a name for that board. So for example, I'm going to take this board, I'm going to put it in truck 101. And so I want the name, human readable name, to be associated with truck 101. So when the data comes in, I can associate that with truck 101. Obviously the data that's being posted up through the website would have to be stored into a database, and so we'd have to kind of build out a schema to store those points. And for example, the GPS points, lat longs, altitudes, the battery percent, the manufacturer model, total distance traveled, and all of that stuff can be associated with the board. And then there's a lot of interesting reports and dashboards you can have. So you should be able to overlay all the points on a map. You should be able to have interesting, reports on how long the board stays at any particular spot, if it was speeding or anything like that. I think that, there's a lot of things that you could do in a dashboard. One other interesting concept is that these boards, right now the configuration is kind of hard-coded on the board itself. And we can have default values on the board in case it ever loses connectivity with the website. But the website really should kind of be the master of this board. And one of the interesting possibilities is you can control the board. So, for example, what is low battery mode? Right now we've got that hard-coded. I think the last time we left it was at 5%. But maybe I want to dynamically send out to all the boards in the fleet that the new low battery mode is 30%. Or the payload size, as we learn more and more about how large the payload should be for optimal battery life, we can modulate that, so we can start to see payloads of not just 1 but say 30 points in a payload. And so there's a lot of interesting things where you can do where the website is actually controlling the configuration dynamically. And finally, with this project coming to an end, if you have any questions on this project, feel free to post comments below. It's been a lot of fun working with this board. I am looking forward to getting on to the ESP32 board that I've got. And, again, if you are interested in a build of the website, an example like a GPS tracker website where, boards can register and then do the tracking and all that stuff, that might be an interesting video series also. As always, if you have questions, comments, leave them below. Otherwise, subscribe for more content like this.